All right, so today we're going to put on our detective hats. But for chemistry, our mission, if you choose to accept it, is to hunt down these incredible secret molecules hidden away deep inside plants. We're talking about compounds that could literally be the key to the next generation of life-saving medicines.
So where do you even begin? I mean, think about it. You've got this plant, right? Maybe it's been used in traditional medicine for hundreds, even thousands of years. But how in the world do you pinpoint that one specific molecule out of a sea of thousands that's actually doing the heavy lifting? The one that has the real healing power?
Well, our little journey of discovery has three main parts. First, we've got to make a chemical map of the place. Then, we find our target compound. And finally, we reveal its molecular ID. Let's get into it.
Okay, so the first step in our detective work is what's called phytochemical profiling. Seriously, just think of it like a detective arriving at a crime scene. The first thing they do is survey the area, right? Get the lay of the land, look for any initial clues. That's exactly what we're doing here.
Now, this first step, it's not going to give us the exact name and address of our molecule. Not yet. But what it does do is tell us what kind of family it belongs to. Are we looking for a suspect from the alkaloid family, or maybe the flavonoids or the phenols? This screening is absolutely crucial because it points our investigation in the right direction from the get-go.
So, how do we get these first clues? Well, we run a bunch of really simple and fast chemical tests. For instance, you've got the Wagner's test. That one's a dead giveaway for alkaloids. Then there's the Shinoda test, which sniffs out flavonoids. Each test is kind of like a little informant, whispering in our ear and giving us a critical lead to chase down.
All right, so we've got our leads. Now we move on to phase 2, what I like to call the meticulous dig. This is where things get really intense. We have to pull our one target compound out of this, complex chemical soup that is the plant extract. And let me tell you, this takes a ton of patience and some serious precision.
First things first, we've got to get the compounds out of the plant. This is called extraction. You can go old school with a method like maceration, which is pretty much just soaking the plant stuff in a liquid. Or you can go high-tech and use something like ultrasound-assisted extraction. That uses sound waves to literally shake the molecules loose, and it's way, way faster.
And the liquid we use for soaking, the solvent, its choice is so critical. It's like trying to open a lock. You need the right key. See, different solvents like methanol or hexane are good at grabbing different kinds of molecules. It's all based on this chemistry rule, like dissolves like. So if you pick the wrong solvent, you might leave the very thing you're looking for behind. No pressure.
Okay, so once we have that raw, messy extract, the real challenge begins: purification. We use this amazing technique called chromatography. It's designed to separate that jumbled up mixture molecule by molecule. It can sort them by size or how sticky they are. I love this analogy. It's like you have a super blurry photo of a huge crowd, and chromatography is the tool that lets you slowly, carefully bring one single face into perfect, crystal clear focus. That's our target.
And that brings us to the grand finale, the most exciting part of this whole thing, the forensic analysis. We've got it. We have our pure compound, our prime suspect, isolated and alone. Now all that's left is to prove its identity, beyond a shadow of a doubt.
Our first go-to forensic tool is called mass spectrometry, or MS. The best way to picture this is to think of it as a molecular scale, but one that is unbelievably precise. It literally weighs our compound and tells us its exact molecular weight. That number is like a fingerprint. It's a fundamental piece of its identity.
Okay, so MS gives us the weight. What's next? We use something called NMR spectroscopy. Now, if MS is the scale, NMR is the blueprint. It's almost like a tiny MRI for molecules. It shows us the whole structure, exactly how every single atom is connected to every other atom, all laid out in 3D space. It's an absolutely mind-blowing tool for figuring out the molecule's complete structure.
So you see how these tools all play together, right? Mass spec gives us the weight. Other techniques can tell us what kinds of chemical bonds are holding the thing together. And then NMR comes in and gives us that final, super detailed map of the whole structure. When you put all that data together, you get a complete profile, a positive ID. Case closed.
So, why do we go through all this trouble? Why does this whole detective story even matter? Well, because this process, this journey from a single leaf to a lab bench and out into the real world, this is the very foundation of how we find new medicines in nature.
I mean, just think about it for a second. Aspirin. That came from willow bark. Some of the most powerful cancer drugs we have, they were first found in the Pacific yew tree. Nature has always been, and still is, our greatest pharmacy. And this whole meticulous, scientific journey is how we take that ancient wisdom and transform it into modern, clinically proven, life-saving medicines.
And that really leaves us with one final, incredible thought. There are millions of plant species out there on Earth. Every single one is its own tiny, complex chemical factory. The next huge breakthrough, the next life-altering medicine, it could be hiding anywhere. Which just makes you wonder, right? What cure is out there right now just waiting to be discovered in the next leaf?